Welcome to Hopkins at Home. So, the agenda for today. As you can see, I've trimmed it from what I originally planned. So we'll go over some very basic physics, a little discussion on measurement that was based off of that reading. It's something that when I TA'd, I would start every class with because I think it brings up some very fundamental points that will also be very fundamental to sensing, since sensing is fundamentally about measurement. Sensor, the whole purpose of it is to measure something. And then we'll go into what we're really covering is what is quantization and what is coherence, because a quantum sensor, it of necessity relies on a quantized phenomena. A more advanced quantum sensor will utilize coherence, which we'll describe. And then entanglement, we're going to leave off until lecture 4. And examples of quantum sensors we'll start with next week. Just a note, it'll come up in the next slide. Physicists and engineers like to work in powers of 10 because it's more convenient. That's a lot easier to write than that or that. Similarly, so that's 1 million is 10 to the 6. 1 millionth is 10 to the minus 6. So the first bit of basic physics, because I want to describe the concept of frequency, we have to talk about a wave. So what's a wave? It's something that's periodic in time or in space. So here we're considering it periodic in time. And it has a period is what time it takes to go from one point to the very same point, however long later. That's the period. So we define the frequency, well, that's just the inverse of the period. So if something is a very long period, it has a very short frequency. And something that's very high frequency, big frequency, very small period. You'll see why we covered that, because light is an electromagnetic wave. What does that mean? What that means is the everyday, when we talk about light, we talk about visible light. But light's actually a spectrum that goes all the way from radio, what we listen to, up to things that have to do with nuclei, gamma rays and X-rays. So these are really high frequency, very short period, and conversely, very short wavelength phenomena. So these very long period, low frequency are very long period. Radio waves are about the size of a building, whereas, microwaves are on the size of a millimeter, so a few hairs. Visible light starts getting to an interesting length scale. So instead of talking in terms of meters, we'll talk in terms of nanometers, which are 1 billionth of a meter. And the reason why that starts getting interesting is because that's when light of that wavelength, how it interacts with matter. And one way that's very, personal to us is when you get on that length scale of light, you get it to about an energy of 10 electron volts. Electron volts is just a unit of energy, like a joule, but it's more appropriate to the atomic world. So we deal with numbers of like 1 to 100 eV rather than joules, which would be 10 to the minus 29 joules, which is awkward. So at 10 eV, well, that light is ionizing radiation. So I don't know if you heard about, all the concern with ultraviolet radiation. And that's because it has enough energy to separate electrons from atoms and molecules and impact DNA. By the way, DNA is on that length scale. And then just rounding this out, showing the action of a prism. So here you have white light coming in, and it refracts the light based off its wavelength. So you can see what the light's made out of. And so prisms, real quick, I can show you something. Just use a spectrometer these days. And it's kind of handy. So you put the light in here with the fiber optic, and on a computer display, I can see what are the wavelengths of light. They cost a few thousand on the low end. I think you can find some really cheap ones on eBay for like $80, a friend of mine was telling me. And I've meant to buy one of those because that'd be kind of cool. To over 100,000, to give you a sense of scale. Those are really high-end spectrometers. And, as we're all familiar with, water droplets can do that for us. And that's how we see rainbows. Wrong way. What am I doing? Okay, here we go. So I hope you all had a chance to read that story, really that story of the carpenter. And if you didn't, I would take a chance to. So I'll start out with the two instruments that are mentioned in that story. First is measuring tape. So this is from McMaster Carr. It's a website that every experimental physicist I know is familiar with. You can buy almost anything you want from there. And here you see the gradations, 1/16 of an inch. Let's just say it's easy to work in round numbers, 1/10 of an inch. And this is made out of metal. Laser interferometer. So how this works, and we'll discuss what coherent is. You need a coherent light source. And you have, this is a beam splitter. So you have the light going here. It bounces off the mirror, comes back, and then bounces off there to the detector. Whereas you have the light is also split, goes off the reference mirror, comes back to the detector, and you count the fringes. So this has a resolution of like a nanometer, well below an inch or a millimeter. Factor of a million, less than a millimeter. And why are these two things significant? Because when you talk about what that carpenter wants to do in measuring the doorway, eyeballing it, measuring tape works. But if he were to use a tool as precise as a laser interferometer, which is not very easy to use, yeah. Oh, this is supposed to be laser interferometer. Oops. Got to fix my slides. I apologize. This is a typo. It's supposed to be the laser interferometer there. You see some interesting physics. That's what's brought out in the story. You see that not only is there always uncertainty in measuring that doorway, that height of that doorway, but that it's a quantity which changes with atmospheric pressure, with humidity, with temperature. And so that means that's not a fundamental quantity. So I don't know if you remember, but as we had the kilogram defined by a big piece of metal in France, and the meter was long ago defined by some standard ruler, you no longer define those quantities in terms of that. And we'll discuss that later, what those quantities are defined in terms of. You define them in terms of something fundamental. And the way we found those fundamental quantities was through quantum mechanics and getting into the atomic world. Say you have two waves, right, and they're completely overlapping, then you see one big wave of the same period. say they're completely out of phase, you slide one of the waves where the peaks or where the troughs are, it's completely flat. And that's how you count the fringes as those two waves slide, as that the wave going on that reference mirror slides against the wave of the measurement mirror. And that's why you need a coherent, which we'll describe eventually, source. So now it's going to get interesting. The idea that things are quantized at a fundamental level is commonly called the early quantum theory. And it was developed about 100 years ago, a little bit more. And underlying that development was the interaction of light and matter. We're going to take 3 examples. And all 3 of these examples have to do, this one is matter radiating light. This one is an electron hitting a piece of metal and emitting light. Oh, sorry, other way around. Light hitting a piece of metal and kicking out an electron. And then the hydrogen light emission, where if you run an electric current, everyone's seen a neon sign. Hydrogen, you can do the same thing. You can fill a tube with hydrogen gas, apply a high voltage, and it glows. And so now you can kind of get an idea, well, what happens when we look at it with a spectrometer? What does that light look like? So starting with blackbody radiation. A black body is something that is a perfect absorber of light. That's why it's called a black body. But we don't need to get into the details of it. We can stick at the level of, I don't know, I'm sure everyone's seen something get white hot or red hot. And so what Planck's challenge was is that how do you explain that through the currently understood laws of physics back then? Something radiating light because of how its temperature. The problem was that the classical model, the model of physics that they had at that time, what it predicted was that the amount of light you would get as the wavelength of the light got smaller and smaller, closer to the visible region, blew up. It's called the ultraviolet catastrophe. And that was because there wasn't the sense that light was quantized, but that light, you could have any frequency you wanted. When Planck introduced the idea that light was quantized and the quanta, or the minimum value of light, we called a photon, well, then he had mathematics that fit the data. And it's something that he struggled with for decades. How can this be that at the smallest level, there's this corpuscular nature to light? The photoelectric effect, which was understood by Einstein through borrowing from Planck. First, let's describe what the phenomena is. And this is really important. So I'll make sure to get to that. This little figure right here. And hopefully it'll make sense to you after I explain it. So what we have is light, and H is Planck's constant. And that was a constant he came up with to describe blackbody radiation. Lo and behold, it shows up in a completely different phenomena. Einstein borrowed it. So what's the phenomena? The phenomena is you can get electrons out of metal by shining light on it. There's a minimum optical frequency or wavelength that you need, depending on the metal, but for whichever metal you have, it's the same. There's a minimum. Below that minimum, so if it's too small in frequency, long in wavelength, low in energy. Those are all synonymous. It's too low in energy, let's say. No electrons are emitted, regardless of the intensity. And then the kinetic energy, or how much velocity the electrons have coming off, that's linear in the energy or the frequency of the illuminating light. And there's no dependence on the intensity. So that's where this figure comes in. What this means is like 2 or 3 low energy photons are not the same as one high energy photon. And that blew people's minds. That, the only way to get this electron out was to have a photon of the right energy or more. But below that, you could have as many as you wanted and it didn't matter. So that's why that effect's really important, because it gives a sense of how light and matter are interacting in a regime that's so foreign from our everyday life. Because, you want to heat something in the microwave. Well, you want it to get, a certain temperature, you can just do it for longer. But with this, you can throw as many microwaves you want. It is a piece of metal and you're never going to get an electron out. So we talked about, I put a prism in the figure. So this is actually an image I got off of Wikipedia, I think, of what a hydrogen lamp looks like, as opposed to, say, a neon lamp. And here, this is a circuit symbol saying we're applying a voltage. And here's a prism, or, our spectrometer. And what's fascinating is that you only see specific wavelengths. You don't see a broad spectrum like you do with a rainbow. And for any hydrogen, you're going to see the same wavelength. You can turn the voltage up as high as you like. It's going to be the same wavelengths. So this is where we get to Bohr. I'm sure, based off of your backgrounds, you're all familiar with this model of the atom. And it has value. It's not completely accurate. So what Bohr's hypothesis was that, and Rutherford developed this a lot as well, that you have this central part that's positively charged, and then you have these negative bits orbiting. And that you can calculate the energy of the electron in its orbit based off of fundamental constants, which we described, one of them being, it shows up again, Planck's constant. And so that's something that is really fascinating. This constant, it came up with Blackbody radiation, came up with the photoelectric effect, and now it's coming up with atoms and them emitting light. So here's a moment for you to calculate this. If you got some pen and paper, here's our expression for the energy of a level. So n can be 1, 2, or 3. I collected up all those constants. It's called the Rydberg constant. It's 13.6 eV. So say we're moving from the 3rd level to the 2nd level. What's that change in energy? And I'll wait for 1 minute, more or less. With his simple model, he was able to explain why we see these discrete lines. And I don't know if any of you had the chance to do this when you were an undergraduate, but yeah, I must have taught this lab, I can't count how many times, but it's a fun one because there's a lot you can do with it. And so now I'm going to use a diagram, which we'll see later on. So we have these 2 levels, these 2 energy levels, and we have that transition from an electron going from that 3rd level down to the second, and it radiates a photon. And so, you know, I can give you an experimentalist's understanding of why this is the case. It has to do with lifetimes. If you don't have a photon, well, this isn't, sorry, here it's decaying. It's not being excited. Say we wanted to excite something from the second level to the third level, we would need a photon of that energy, right? Say we had a handful of photons that kind of added up to that energy. They would all have to be there at the same time. And, well, I don't know if anyone's ever tried that, but I'm starting to confuse myself, so I'll stop. So we've covered quantization, and this is at a pretty good clip. So now it's going to get a little bit trickier. So now we've covered quantization. That, well, the first part of it, the quantization of energy, the quantization of light. Now we're going to start getting into the quantization of something a bit more esoteric. So this was understood first by the Stern-Gerlach experiment. I'll go over what it is. And this is actually their published data right here. I pulled it out of their paper. Their paper's in German, so couldn't read it. So you have an oven where you heat up silver, and then you use these plates to collimate it to make a beam. And then here they have a magnet where it's not a homogeneous field. So it's not like all the magnetic field lines are going from one plate to another, but these lines are spreading out because you've shaped the North Pole such that it's at a point. And when you have something, the reason why they chose silver is because silver is neutral. It's not electrically charged. They didn't want to use ions because if you have a charged particle in the magnetic field, I'll show you an example of it in the next slide, its trajectory will bend. It'll be accelerated. They didn't want to deal with that effect. They wanted to just look at something called spin. And so what we mean by spin is these particles in the subatomic world, be they photons, be they electrons, be they nuclei, they have this quantized angular momentum. And the reason why we know that is because their experiment. Because if the spin could take any value, you would just get a smeared out line. But instead, what they saw was there were two sides. It's not as dramatic as the image in this cartoon. Nothing really is. But what it showed is that it's either up or down. And so based off of the direction of that angular momentum, it defines how it interacts with that magnetic field, which it might not be surprising to us as it was to them because, you know, we've grown up in a world where there's this idea of quantum mechanics, things are quantized, there's atoms. But they didn't grow up in a world like that. They grew up in a world where matter was continuous. The spin of the electrons, you know, so the first example was dramatic, but this is pretty much getting us to where we want to be when it comes to spin. So electrons have a magnetic moment. You can think of that as like, I don't know if you heard of like a moment of inertia, or it just has to do with, you can think of it as an analog to mass. So like a magnetic inertia. And some have conceptualized it as, you know, the electrons spinning. And you can see this in the response of electrons to magnetic fields. So you can't see it, but there's a big coil here. And what this is an evacuated tube with a little bit of some type of gas like neon or not hydrogen. That's a bad idea. Neon. And so you can see the path of the electrons in the tube. And this is actually a classic experiment that's also done in undergraduate laboratories. It allows you to measure the charge to mass ratio of the electron by the radius of that curvature. So we didn't really go over it, but you know, there was this debate hundreds of years ago between Newton and someone else about whether light was a particle or whether it was a wave. And what we see is that light can behave as both. But we can also see that with matter, that you can actually, we talked about the fringes with light. Well, you can get fringes with electrons. And this is de Broglie's matter wave hypothesis. And the reason why I wanted to bring this up is because the concept of spin will be very important for us as we move on. And the way I like to think of spin is that I'm sure, you know, you're maybe familiar with polarized sunglasses, you know, where, I don't know if you ever have taken two polarizers and crossed them, and then you can't see any light. Has anyone tried that? I was bringing that up because the polarization of light, that orientation of light, you can kind of, light has angular momentum, and polarization is one way we understand it or describe it. And so there's a wave with angular momentum, which is, that's very novel, because when we think of momentum, we think of something with mass, right? It has inertia. But now we're talking about things like light that don't have that. And so, you know, electrons aren't really a point. They're more like a distribution, a wave. And so when we think of the spin of electron, I kind of think of it as like the polarization or the angular momentum of that wave. And this is all very relevant because when we talk about magnetic resonance imaging, MRI, we're talking about those spins. And that's how we image inside ourselves. And that's what we'll be talking about next week. And that was really developed in the 50s and 60s. The science of it was, but the techniques weren't developed until the 70s and 80s. But the science was developed in like the 50s and the 40s. And it's still relevant. When you talk about quantum computing and quantum sensing, essentially what we're doing is stuff that you do with MRI, because you're manipulating nuclear or electronic spins. So one final thing with spins, and this is part of the challenge of a course like this, but I think that you as a group are well positioned given your background, because I think these aren't the first time you've heard these words. But I wasn't able, I had a very nice top, but I lost it. And I was able to find something that I could use as a top. This is a base for an optical post. So we've talked about how these things have spins. Well, what happens when you put these spins in a magnetic field? Well, they precess. So the tops spin around that magnetic field. And so let's see if I can do this demo. Yeah, you see how that's precessing? Well, that's precessing. The tops that we play with are precessing because of Fg, the force of gravity. The spins in the quantum mechanical world precess because of magnetic B field, or magnetic field. Sorry, that's where my everyday language slips out. Oftentimes, magnetic field is called the B field, but the magnetic field. We're getting close to something interesting, so bear with me. So we talked about the, finally, to coherence. So waves are characterized by a period, which we talked about, an amplitude, but also a phase. Like when we talked about if the red and the blue waves completely overlap and you added them together, then you're just going to have one wave of twice the amplitude. Whereas if where the red peak is where the blue minimum is, it completely flattens out. That relative position of two waves is called a phase. So this is a very technical sentence. When you have correlation in wave properties in time and space, that's coherence. So with our coherent light source, you have a coherence length, which means this wave, this light wave, it maintains its phase and its frequency over a certain length. And that's actually what limits the ability to have an interferometer, is how clean that tone is of light. And we described it as a tool for metrology, but well before it was ever used for that, it was used to understand the coherence of sources. And so we talked about the fringes, right? So here's the maxima and the minima of an interfering light wave that goes through a double slit. Well, you can do the same thing with electrons. And that's why we talk about them both being waves. That wave nature of the electron and of atoms is at the root, I would argue, of their spin properties. And it's those spin properties that are most often used in quantum sensing, because it's so fundamental. What I haven't, I'll leave it for later. So we talked about coherence, talked about spin, doing pretty good for time. Spin coherence, and then we'll get into this. There's two primary time constants for spin coherence. So what that means is those spinning electrons or spinning nuclei, how long do they stay together as they spin? And how long do they stay together with that top? And these two time scales and differences in those time scales is how we can image inside the body. And we'll talk about that. And so just as a quick demo, so when you talk about T1, oh, it spun off. But that's like how long your spinning top stays spinning before it falls down. T2 is if I had a bunch of these tops and they're all spinning, how long they spin together before they get all decohered and all garbled up. Those are the two fundamental spin coherence times. Last slide. So we've talked about quantization. We've talked about coherence And typically we're talking about spin coherence. Yes, it is the same T1 and T2 as in T1 and T2 weighted MRIs. That's it exactly. And you see now why I left off entanglement. No way we were going to get to that. We'll talk about that in lecture 4. And this is one of those coherent manipulation sequences, and hopefully by next lecture, the end of it, you'll understand what that means, how we interrogate T1 and T2 times, spin coherence times. This is a Rydberg atom, and you can use that as a sensor for magnetic fields, for electric fields, and they're shining a laser in there. And what a Rydberg atom is, remember we talked about the Rydberg constant? It's an atom with a highly excited electron, so it effectively acts like the hydrogen atom, so it's easy to use. This is some kind of magnetic optical trap for ions, and that's how we get very precise clocks. And clocks are extremely important, and we'll talk about in lecture 3 how we get clocks and what we use clocks for. The internet, GPS, cell phones, practically everything need clocks. And this is something closer to MySpace, and we'll talk about that later. So next week will be magnetic fields. I'm going to focus on using atomic vapors for measuring magnetic fields, and also just like the basics of MRI, because that's something that everyone knows what that means.